All right, so if we're talking about definite integration, this is the very basic reason, the very basic function of definite integration is to find the area under a curve. The applications of definite integration are just all over the place. But at the very core of definite integration, you're looking for the area under a curve. So maybe I wanted to look for the integral from, let's say, 0 to 4 under the curve of x squared dx. So first of all, what is this going to look like? Well, x squared is just a regular parabola, so it's going to look something like that. And the 0 to 4 means I'm looking for the area between 0 and 4. So I'm looking for all this area. So keeping in mind that the integral is that whole limit summation function for adding up all the infinite number of rectangles under the curve and all that jazz, this is just a lot easier because all I would do is I would integrate this x squared, which would be x cubed over 3. Now I can use this plus c, but we're going to talk about that because the integral of x squared is x cubed over 3 plus c. And I want to keep this 0 to 4 here. That means that this notation says that I have integrated it, but I have not used the upper and lower bounds yet. So the fundamental theorem of calculus says that I first substitute in this 4 in for x, which would give me 4 cubed over 3 plus c, and then I would subtract, so this is substituting 4, then I would subtract when I substitute 0 into the function, which would be 0 cubed over 3 plus c. Now the cool thing about this is, if I were to get rid of the parentheses, 4 cubed, I believe, is 64 over 3 plus c minus 0 minus c. When we do this, these c's end up canceling out, and they will always cancel out if you're doing definite integration. So if you're doing indefinite integration, if there are no upper and lower bounds, you need the plus c. If you are not using or if you are using definite integration, you really don't need this at all, because they will always cancel out because of the fundamental theorem of calculus. In which case, 64 thirds minus 0 is just going to equal 64 thirds. So the area under this curve is 64 thirds. 16 times 4 is 40 plus 20. Yeah, it's 64. So the area under this curve is exactly 64 thirds. Now, if you put triangles or rectangles in here, you would get an approximation. But the limit of that approximation, as the number of rectangles increases, will approach 64 thirds. So that is the exact area under that curve. Maybe we wanted to do something like the integral from 0 to, let's say, pi of cosine. So the integral from 0 to pi of cosine x dx. I don't want you to do cosine, I want to do sine. So first of all, what is this looking like? Well, we know sine looks like this, where that's pi. So if I'm integrating from 0 to pi, I'm looking for the area under the curve right there. Okay, so the first thing I want to do is the derivative of what is sine. Okay, well, the derivative of cosine is negative sine. So this integral would be negative cosine from 0 to pi. Now I can check myself. The derivative of negative cosine will be positive sine, because the derivative of cosine is negative sine, so the derivative of negative cosine would be positive sine. This all works out. Fundamental theorem of calculus says that I substitute these values in, and I look at the negative cosine of pi minus the negative cosine of 0. That's a beta. It should be 0. Okay. Notice I'm not putting in the plus c because they will cancel out. In this case, the cosine of pi is negative 1, so this is negative 1, which is positive 1. The cosine of 0 is positive 1, so I'm subtracting a negative 1, which is plus 1, which equals 2. Fantastic. The area under this curve is exactly 2, which is pretty darn cool. So really that's it. I mean, they can get, let's do this. Maybe I want to look at the area under the curve of, let's do sine. But I want to say from pi over 2 to 3 pi over 2. So this would be, we know sine, no, I'm going to use cosine this time. I'm confusing myself. This time I'm going to use cosine because this looks like this. So if I'm going from pi over 2 to 3 pi over 2, I'm looking for this area. All right, cool. Where's my x? There's my x. This is below the line. This is going to turn out interesting. So the derivative of what is cosine? The derivative of sine is cosine. So I'm going to be looking at sine of x from pi over 2 to 3 pi over 2. Now if I substitute, using the fundamental theorem of calculus, if I substitute 3 pi over 2 into this, I get the sine of 3 pi over 2 minus the sine of pi over 2. The sine of 3 pi over 2 is -1. The sine of pi over 2 is +1. Well, this is interesting. This is -2. Now, why is it negative? Because area shouldn't be negative. Well, it's because we're looking at the area under the x-axis. So if we look at the area under the x-axis, it's negative area, which, let's look at something else. Maybe we want to look at the integral from 0 to pi of the sine of x dx. If we do this, we're looking at, no, I want to use cosine. Why do I keep messing this up? The cosine, because cosine looks like this. If we're going from 0 to pi, we're looking at this area and this area. So the cosine, this integral would be sine of x from 0 to pi. If I substitute pi in, I get the sine of pi minus the sine of 0, just 0, not theta. Now this is going to be the sine of pi is 0 and the sine of 0 is 0. This area ends up being 0. Well, that's strange. Why is it this way? Because this amount of area is the exact same as this amount of area. This area is positive and this area is negative. They end up canceling each other out. So you have to be careful about the problem you're working with when dealing with things like this, because this definitely does have a positive area, and yet, or I should say a non-zero area. And yet we ended up with an area of 0. It's because the positive part cancels with the negative part. Cool.